Natural Language Processing and Computer Vision. About this course. Every day, computers help you by understanding things they hear and see. Your phone responds to your verbal questions and commands. Traffic management systems observe streets and highways to suggest ideal routes for you to travel. Computers respond to your needs and help you make good decisions. Think of artificial intelligence, AI, as prediction machines that augment human intelligence and provide insights. Welcome to the Natural Language Processing and Computer Vision course. In this course, you'll become familiar with fascinating artificial intelligence, AI, concepts, such as natural language processing, NLP, and computer vision. You'll learn how chatbots respond to your questions, and other ways that computers augment human senses. Learning objectives. After completing this course, you should be able to define natural language processing. Explain how AI uses natural language processing to derive meaning from text. Explain the classification problem and its solutions. Describe how a chatbot understands, reasons, learns, and interacts with users. Distinguish between intents, entities, and dialogs. Identify appropriate uses for chatbots. Identify real-world uses for natural language processing. Describe how AI classifies images to derive meaning from them. Describe how a convolutional neural network, CNN, analyzes an image. Describe how a generative adversarial network, GAN, creates a credible image. Identify real-world uses for computer vision. About this module. Module 1. The Debater Project. Introduction. In this module, you'll learn about how IBM Project Debater demonstrates what natural language processing, NLP, is and what it can do. Learning objectives. After completing this module, you should be able to define natural language processing. Project Debater. Can an AI win an argument? IBM Watson winning Jeopardy! If you ask an artificial intelligence system a question on a topic for which it's been trained, it can look up an answer. The quiz show, Jeopardy! Proved that years ago. But can an AI system carry on a continuing conversation and respond to what is said with each exchange? Let's make this question even more difficult. Can an AI win a debate with a human expert about a complicated topic? To answer this question, consider a famous experiment, then learn how AI works with spoken and written language. IBM began developing Project Debater in 2012, hoping to build a machine that could do more than win debates with humans. In other words, IBM Project Debater would need to be able to do more than just answer questions in a human language. It would need to have the ability to listen to a series of competitive arguments posed by humans and respond to them intelligently. IBM's ultimate goal was to build a system that could help people make evidence-based, bias-free decisions on difficult topics where the answers aren't obvious. Debate steps. Students debating in a classroom. It takes 4 steps to win a debate. To get a feel for what winning a debate requires, try putting yourself in the AI's position. What would it take to enable you to intelligently debate a human opponent? Now, take a moment to learn more about what is required for each of the debate steps. To learn more, select each step a debater AI system must take. Step 1. Learn and understand the topic. Ingest several billion passages from newspapers, books, and journals. AI researchers call this collection of learned material a corpus. Then, structure all that content so you can relate concepts to each other and evaluate them, even when they're stated in different ways. Step 2. Build a position. Create an opening speech made of short pieces of text pasted together from the corpus. Your speech should detail your position on the debate topic. It can't be a jumble of phrases. It must present a compelling argument, in logical order, using good grammar. Step 3. Organize your proof. Learn the deeper meaning of the facts that surround your topic. Decide what evidence is strongest and arrange your proof by themes. Adjust your arrangement each time new evidence arrives. This will help you find updated or completely new information that can score points against your opponent's position. Step 4. Respond to your opponent. Listen to your opponent's arguments and rebuttals, then deliver a convincing rebuttal that refutes your opponent and further proves your case. Why do we care about these 4 steps? Because they reflect and test 4 things that cognitive systems do. Cognitive systems understand, reason, learn and interact. Understanding, cognitive systems understand like humans do. Reasoning, they reason underlying ideas and concepts. They debate. They infer and extract concepts. Learning, they never stop learning. Advancing with each new piece of information, interaction, and outcome. They develop expertise. Interacting. Allowing them to interact with humans. Steps in natural language processing. Is it difficult to understand human language? Understanding human language is difficult, even for people who have grown up with it. Human language is incredibly complex, full of strange expressions that seem to contradict each other, metaphors that require cultural knowledge to understand, and grammatical structures that sometimes turn simple ideas into tongue twisters. Machines require systems that research scientists call natural language processing, or NLP, to understand human language. IBM Project Debater was the most complex AI system IBM Research had ever built to understand human language. IBM Project Debater, we should subsidize preschool video transcript. So, now we move on to round 2, rebuttals. And, again, each side will have 4 minutes to respond to the opponent's arguments. First, with her rebuttal, Project Debater, arguing for the resolution, we should subsidize preschool. Thank you, again. For starters, I sometimes listen to opponents and wonder, what do they want? Would they prefer poor people on their doorsteps begging for money? Would they live well with poor people? Without heating and running water? Giving opportunities to the less fortunate should be a moral obligation of any human being, and it is a key role for the state. To be clear, we should find the funding for preschools and not rely on luck or market forces. This issue is too important to not have a safety net. Next, I think that Harish Natarajan raised the following issue: there are more important things than preschools to spend money on. The state budget is a big one, and there is room in it to subsidize preschools and invest in other fields. Therefore, the idea that there are more important things to spend on is irrelevant because the different subsidies are not mutually exclusive. I believe the following example from a related field will explain what I'm trying to say about subsidy policies. Research shows that childcare subsidies to low-income parents enable those parents to enter and remain in the workforce. To be clear, my intention is not to leave a suitcase full of money for everyone to grab at will. We are talking about a limited, targeted and helpful mechanism. Whether or not you agree with IBM Project Debater's position in this debate, IBM Project Debater rebutted its opponent with clear and well-argued statements, complete with examples and even a metaphor. This is a major step forward in the field of natural language processing. IBM Project Debater was a success. Gradually, this artificial intelligence grew more skilled until it could regularly win debates. Once again, this was a major step forward in the field of natural language processing. About this module. Module 2. AI performs natural language processing. Introduction. In this module, you'll learn how natural language processing, NLP, breaks sentences of human language into entities and their relationships, distinguishes between human emotions and sentiment, and resolves the meaning of confusing expressions. Learning objectives. After completing this module, you should be able to explain how AI uses natural language processing to derive meaning from text. Explain the classification problem and its solutions. NLP sentence segmentation and tokens. Natural language processing. Computers are best at working with structured data, in which everything is neatly grouped and labeled. Unfortunately for machines, human language is anything but structured. You've been using language for most of your life. Your brain accomplishes this through some of the most complicated neural circuitry on Earth. But it is very difficult to create machines that can work with human language. Understanding natural language video transcript. Getting machines to understand our human language is one of the hardest tasks in artificial intelligence today. Languages are nuanced and complicated and present difficulties for computers that are used to fixed rules. Language can also be easily misinterpreted. Take the famous Groucho Marx quote, "One morning, I shot an elephant in my pajamas. How he got my pajamas, I don't know." To actually understand what is being said is really hard for the computer to do. What we try to solve through the field of natural language processing is to start cracking what does he mean when we use these words and sentences. How are sentences related to one another? Is this word close to this other word and why? So, that is a field that for us is so easy. It's very hard for computers to do. In NLP, machines segment sentences and extract meaning from tokens of human language. Human language is unstructured. Although it is loosely held together by rules of grammar, our language expresses information in many confusing ways. Unlike structured information, which can be arranged in tables or matrices with neatly labeled rows and columns, unstructured information is messy and difficult to understand. To see why, consider this famous joke by Groucho Marx. "One morning I shot an elephant in my pajamas. How he got in my pajamas, I don't know." Adapted from Groucho Marx, 20th century comedian and movie star. To deal with the messiness of unstructured information, computers begin with one sentence at a time. This is called sentence segmentation. Computers then break the information into small chunks of information, called tokens, that can be individually classified. Once the tokens in text have been sorted into a structure based on what they mean, NLP can work with them. The following activities show you how Groucho Marx's joke can be tokenized into useful categories called entities and relationships. You'll learn the meanings of these words as you continue. Activity 1, Entities. Drawing of an elephant. An elephant. An entity is a noun representing a person, place, or thing. It's not an adjective, verb, or other article of speech. Recall Groucho Marx's quote, "One morning, I shot an elephant in my pajamas. How he got in my pajamas, I don't know." Activity 2, Relationships. Drawing of the same elephant, now wearing human pajamas. The same elephant, now wearing human pajamas. A relationship is a group of two or more entities that have a strong connection to one another. An entity is a noun representing a person, place, or thing. It's not an adjective, verb, or other article of speech. Recall Groucho Marx's quote, "One morning, I shot an elephant in my pajamas. How he got in my pajamas, I don't know." Spoiler alert! Elephant, and pajamas are entities because they are nouns. Shot, an, in, and my are not entities because they are not nouns. Exit course. Natural Language Processing and Computer Vision. 100% complete. Course Overview. About this course. Earn a credential. Course Design. Module 1, The Debater Project. About this module. Project Debater. Debate Steps. Steps in Natural Language Processing. Quiz. Module 2, AI performs natural language processing. About this module. NLP sentence segmentation and tokens. Emotion detection and sentiment analysis. The classification problem. NLP and Jeopardy. Quiz. Module 3, Chatbots use NLP to interact with humans. About this module. Chatbot structure. The chatbot backend. Intents, entities, and dialogue. Example NLP analysis. Quiz. Module 4, AI classifies images. About this module: convolutional neural networks, generative adversarial networks, computer vision applications, quiz, summary and final assessment. You've come so far. Key points to remember. Explore more. Final assessment. Course completion. Lesson content. Lesson 9 of 25. NLP sentence segmentation and tokens. Natural language processing. Computers are best at working with structured data, in which everything is neatly grouped and labeled. Unfortunately for machines, human language is anything but structured. You've been using language for most of your life. Your brain accomplishes this through some of the most complicated neural circuitry on Earth. But it is very difficult to create machines that can work with human language. Watch this video to see how research scientists approach this problem. Video transcript. Understanding Natural Language Video Transcript _and.pdf. 20.4 KB. In NLP, machines segment sentences and extract meaning from tokens of human language. Human language is unstructured. Although it is loosely held together by rules of grammar, our language expresses information in many confusing ways. Unlike structured information, which can be arranged in tables or matrices with neatly labeled rows and columns, unstructured information is messy and difficult to understand. To see why, consider this famous joke by Groucho Marx. Photo of comedian Groucho Marx. One morning I shot an elephant in my pajamas. How he got in my pajamas, I don't know. Adapted from Groucho Marx, 20th century comedian and movie star. To deal with the messiness of unstructured information, computers begin with one sentence at a time. This is called sentence segmentation. Computers then break the information into small chunks of information, called tokens, that can be individually classified. Once the tokens in text have been sorted into a structure based on what they mean, NLP can work with them. The following activities show you how Groucho Marx's joke can be tokenized into useful categories called entities and relationships. You'll learn the meanings of these words as you continue. Activity 1, Entities. Drawing of an elephant. An elephant. An entity is a noun representing a person, place, or thing. It's not an adjective, verb, or other article of speech. Recall Groucho Marx's quote, "One morning, I shot an elephant in my pajamas. How he got in my pajamas, I don't know." Select then drag and drop the words into their corresponding category. Hint: 3 of the words can be tokenized as entities. Select for a spoiler alert. I, elephant, and pajamas are entities because they are nouns. Shot, an, in, and my are not entities because they are not nouns. Activity 2, Relationships. Drawing of the same elephant, now wearing human pajamas. The same elephant, now wearing human pajamas. A relationship is a group of 2 or more entities that have a strong connection to one another. Recall Groucho Marx's quote, "One morning, I shot an elephant in my pajamas. How he got my pajamas, I don't know." Spoiler alert! For I and elephant, I and pajamas, and elephant and pajamas, both words in the pair are nouns and are related entities. I and shot is not a relationship between entities. I is a noun but shot is a not. In and pajamas is not a relationship between entities. Pajamas is a noun but in is not. Once an AI has classified entities and relationships in text or speech, the AI can begin structuring the information as a step toward understanding it. Your brain, by the way, does the same thing, which might have helped you find entities and relationships in the previous activities. For example, consider the following 2 sentences: Armin broke the glass. He always breaks the glass. Notice that there is a relationship between the 2 sentences. The word he is related to the word Armin. The machine uses NLP to identify this relationship. Activity 3, Concepts. The same elephant in pajamas, now wearing a safari hat. The same elephant in pajamas, now wearing a safari hat. A concept is something implied in a sentence but not actually stated. This is trickier because it involves matching ideas rather than the specific words present in the sentence. Recall, once more, Groucho Marx's statement, "One morning, I shot an elephant in my pajamas. How he got my pajamas, I don't know." Based on this statement, select the words that are concepts implied, but not stated. Hint: 3 are implied, and 1 is stated. Safari. Correct. When Groucho says he shot an elephant, either with a weapon or we hope with a camera, it's possible that he's referring to a safari without using that word. Photographed. Correct. When Groucho says he shot an elephant, it's possible that he's referring to photographing rather than shooting the animal. Pajamas. No, this word isn't implied. It's stated in the sentence. Rifle. Correct. When Groucho says he shot an elephant, it's possible that he's referring to a rifle or some similar weapon, without using that word. By the way, in real life, Groucho was well known for his kindness to animals. Emotion detection and sentiment analysis. Emotion detection and sentiment analysis are not the same thing. Although emotions and sentiment deal with feelings rather than facts or actions, distinguishing between them can help an AI better understand a sentence. Graphic of a sentimental heart next to an angry lightning bolt. Emotion detection identifies distinct human emotion types. For example, you can determine if the emotion being expressed is anger, happiness, or fear after reading a user's rating and comments in an online customer satisfaction survey. AI can be trained to classify emotions. Identifying the right emotional token can make a big difference when an AI system is reading a social media post or a customer service chat, in which different emotions significantly change the meaning of a sentence. Graphic of a horizontal scale from 1 to 10, with the sentimental heart at one end and the angry lightning bolt on the other. Sentiment analysis isn't a specific emotion, at least, not as computer scientists use the term. Instead, it's a measure of the strength of an emotion. You can think of sentiment as a sliding scale between positive and negative, with neutral in the middle. Sentiment analysis is a means of assessing if data is positive, negative, or neutral. The classification problem. Human language makes classification challenging. Cartoon-style graphic of a nose supported by running feet. Here's an old-fashioned riddle. Why does your nose run and your feet smell? Human language is full of terms that are vague or have double meanings. This is called a classification problem. In the riddle, run and smell each have two meanings. A runny nose means you have a cold and you need a tissue to wipe your nose. A smelly foot means that your foot has an unpleasant odor. It might only take you a moment to understand the joke, but an AI system might have difficulty classifying its elements. Consider these examples. You can ship a box by train. When a building burns down, it burns up. You can fill in a form by filling it out. A wise guy is not the same as a wise person. Classification can be more difficult for an AI system than identifying tokens because so much of classification depends on the context in which a sentence is contained. Compare I went to the docks to ship my box to I went to the station to ship my box. Both sentences indicate where a box's travel begins, but neither specifies how it will travel. An AI system must associate the word ship with either the word station or docks, and then relate that association with the right concept, either train or boat. How does an AI system deal with this problem? After ingesting several thousand instances in which shipping from a dock results in boat travel, while shipping from a station leads to shipping by rail, the AI system identifies the frequency in which places and kinds of travel are linked. Gradually, the system gets better at classification and makes fewer mistakes. However, as with humans, an AI system's classification will never be 100% perfect. That's why well-designed AI systems give not only a response, but also a confidence value. As you've learned, getting from tokens and classification to answering questions, or winning a debate, is a complex endeavor. But it isn't enough to take a machine all the way to understanding. You will learn about ways to do this later in this course. NLP and Jeopardy! The process works. Watch this video to see IBM Watson win the television quiz game Jeopardy! Playing against human grand champions. It's fun to watch and will give you a quick review of natural language processing. Watson on Jeopardy! Video transcript. A little over 3 years ago, the folks at IBM came to us with a proposal that they considered to be the next grand challenge in computing, and that was designing a computer system that could understand the complexities of natural language well enough to compete against Jeopardy's best players. One of the first major breakthroughs in natural language processing came when IBM developed an AI named Watson to take on the television game show Jeopardy! Watson didn't come out of the box ready for prime time. Yell barracuda, everybody says what? You. Yell shark, we've got a panic on our hands is said in this film. Watson. What is the 4th of July? No. Max. What is Jaws? Thank you. 4th of July. The IBM team took years developing, refining, and training the system, including months of practice. Matches on a mock set. Founded in 1789, this Washington, D.C. school was the USA's first Catholic college. Sorry, I'm stumped. Oh. To make Watson a contender, the IBM team armed the system with advanced math called algorithms and powerful AI technologies like machine learning. In February 2011, it was time for Watson's TV debut to show the world what it had learned. Even a broken one of these on your wall is right twice a day. Watson tries to understand the question by breaking it down into different parts of speech. It then does a broad sweep of the millions of books, articles, and documents that cover the wide variety of Jeopardy! Topics to come up with thousands of possible answers. Watson then collects, analyzes, and weighs evidence from all the material to narrow down these possibilities. Thousands of different algorithms work together to score the evidence for each possible answer, then Watson ranks the remaining possibilities by its confidence in those answers. All this happens almost instantaneously. Watson. What is a clock? Clock is correct. What is Christchurch? Jeff. Who is Leo Tolstoy? Yes. Who is Henry VIII? Yes. What is narcolepsy? You're right again. And with that you moved to $36,681. A big lead. In a watershed moment, Watson took on and defeated the world's 2 top Jeopardy! Players. Who is Stoker? I for one welcome our new computer overlords. The team at IBM knew this technology could do far more than win game shows. Watson on Jeopardy! Was just the beginning. This technology could be unleashed on some of the world's most difficult problems by helping industries that are flooded with data. If that was possible, what else could we do? Now that you have a basic understanding of the mechanisms behind natural language processing, continue reading to learn how a simple form of NLP drives the chatbots you've probably encountered when clicking the chat button on an internet shopping site. About this module. Module 3. Chatbots use NLP to interact with humans. Introduction. In this module, you'll learn how a chatbot listens to a user's questions and generates useful answers. Learning objectives. After completing this module, you should be able to describe how a chatbot understands, reasons, learns, and interacts with users. Distinguish between intents, entities, and dialogs. Identify appropriate uses for chatbots. Identify real-world uses for natural language processing. Chatbot structure. If you've clicked a chat button online and encountered a non-human chatbot, you might have noticed 2 things. When you ask a clear question that relates to the website's purpose, like asking a shopping chatbot how can I get a refund, it usually gives you a response related to your question. When you ask a question that's unclear or unrelated to the website's purpose, like asking the shopping chatbot got any tickets for sister, the response will be more along the lines of I'm sorry, I didn't understand your question. This happens because the chatbot is programmed to answer only limited questions about a particular subject. Graphic of cell phone connected electronically to a chatbot. Even with this limitation, chatbots are useful in fields ranging from retail sales to immediate care medicine. You can engage with a chatbot online at any time. A chatbot is always ready for your question, even if it cannot answer you. Some institutions use chatbots often because they don't just broadcast ads like TV commercials. When people engage with them, chatbots listen, and they answer repetitive questions that a business would otherwise need to pay humans to handle. Chatbots work with small data. This means their scale is much more limited. A movie chain's chatbot might need to answer questions only about movie titles, locations, and times, while a more general AI that searches social media might need to answer broad questions about what millions of people think. AI researchers say that chatbots snack on small data. A chatbot has a frontend and a backend. Diagram of a box containing the title frontend and the phrase user interaction, connected to a box containing the title backend and the words logic and data. The frontend of a chatbot is the messaging channel. The frontend interacts with the person who's asking questions, both listening, or reading, and speaking, or presenting text. The backend of a chatbot is where the hard work takes place. The backend operates application logic and has enough memory to remember earlier parts of a conversation as dialogue continues. The chatbot backend. A chatbot's backend does the hard work of understanding and responding. Suppose part of a chatbot's job is to help you when you've lost or forgotten your password. You might enter, "How do I reset my password?" which would be easy for the chatbot to handle. To describe that action, a chatbot programmer might think in terms, such as, if question equals "How do I reset my password?" then reply equals "Here's how to create a new password." But humans are not always easy to understand. They might ask or type, "How come I can't log into my account? I forgot my @number password. It says my password is wrong. Forget password." This tells you that one chatbot response, "This is how to create a new password," can be triggered by a large number of user queries, including all those listed, and more. Graphic of many lines of random text converging onto one side of a circuit board, but only one line of text coming out the other side. This is a great job for algorithms called classifiers. Classifiers can map many different ways of asking a question to a very small set of answers. How small? Some retail chatbots respond to hundreds of different questions with only 5 or 6 possible answers. Questions the chatbots can't answer are sent to human customer service representatives. Intents, entities, and dialogue. A chatbot backend usually includes 3 parts: intents, entities, and dialogue. Graphic of the frontend/backend diagram, now with the backend section divided into 3 parts titled intents, entities, and dialogue. Chatbots understand a question by breaking it into parts and relating those parts to things in its memory. A chatbot's goal is to identify what are called entities and intents, then use what it's found to trigger a dialogue. What do these terms mean? Intent. An intent is a purpose, the reason why a user is contacting the chatbot. Think of it as something like a verb, a kind of action. A user might intend to file a complaint, to ask for directions, to speak to a salesperson. An institution might have many customer or member intents that it would like a chatbot to handle. Suppose you've been hired to help create a chatbot for a restaurant chain. One possible intent would be to find out when the restaurants are open. You might first interview a person who previously handled many forms of this question on the phone. Then, your task would be to list all the different ways a caller might ask about when the restaurants are open. The following table provides many examples of possible user inputs that map to this kind of intent. For the open intent, some possible user inputs include, "When do you open?" For the open intent, another possible user input is, "What are your hours?" A user might also ask, "You open now?" to express the open intent. Another variation for the open intent is, how late are you open? Finally, a user could ask, can I walk in at 7 p.m., to trigger the open intent. Once you have a list of the intents you want your chatbot to fulfill, you're ready to continue. Entity. An entity is a noun, a person, place, or thing. This concept was covered earlier in this course. If a user asks, what are the hours for the Austin location, then providing business hours is the intent and Austin is the entity. A chatbot needs a full list of entities in order to be helpful. The following table lists examples of entities that map to the intent and possible user inputs of the previous restaurant chain example. For the open intent, a possible user input is when do you open, which maps to the Austin entity. For the open intent, a possible user input is what are your hours, which maps to the schedule entity. For the open intent, a possible user input is you open now, which maps to the time entity. For the open intent, a possible user input is how late are you open, which maps to the time entity. Summary note. And so forth. There are many inputs mapping to this intent, just as there are many entities implied by this intent. Now that you've learned about entities and intents, let's talk about dialogs. Dialogue. A dialogue is a flowchart and if/then tree structure that illustrates how a machine will respond to user intents. A dialogue is what the machine replies after a human asks a question. Even if a human uses run-on sentences, poor grammar, chat messaging expressions, and so on, artificial intelligence allows the NLP to understand well enough to provide a response. Graphic of a flowchart branching upward like a tree. The dialogue represents each possible word or phrase a user might enter, the matched response for the chatbot, and the many possible subsequent replies a user might make next. That's too much for an ordinary flowchart to show, you might need 3 or 4 dimensions, so chatbot software condenses each moment of the conversation into a node. A node contains a statement by the chatbot and a long, expandable list of possible replies. Planning this flowchart would be an adventure. You'd need to assign a reply to every possible user input after the chatbot's greeting. For the restaurant hours example, all possible questions about a restaurant's hours would lead to a single reply. This would continue for the next question, perhaps for the restaurant's address, and so on. A large number of possible questions would be mapped onto a small number of possible answers until the conversation is ended. Spoiler, it helps that today's virtual assistants already have been trained on Wikipedia, so they know, for example, the difference between a wise man and a wise guy. Example NLP analysis. Intents, entities, and dialogues make quick work for NLP. In a conventional computer, the program code is stupendously large but wouldn't handle intents, entities, and dialogues very well. A conventional computer would need a separate if/then line for many thousands of ways a question might be asked. Unless a human were to match one of those lines perfectly, the computer would fail. But an AI system's combination of NLP with intents, entities, and dialogue can make quick work of this. NLP analyzes sentence components, then uses processes like passage and evidence scoring to classify the sentence components against possible chatbot responses. The result is that when a human user asks a question, the AI system provides the answer with the highest confidence. Graphic of the Staples Easy button. Consider Staples, the office supply company that features the Easy button. Suppose a customer asks for a chatbot on Staples' website. The chatbot's frontend receives the customer's inquiry, then forwards it to the chatbot's backend. There, IBM Watson Assistant runs the NLP to understand the human's intentions regarding ordering a product or tracking a shipment. If the customer says, "I want to reorder black pens," the chatbot figures out what that means. Then, it uses cognitive services to pull up the customer's purchase history. Within seconds, the system is helping the customer buy more pens. The Staples chatbot only knows 5 things, but it knows them well. It supports online sales 24 hours a day, giving callers round-the-clock service while leaving human staff free to do other work. This is valuable for both the customers and the business. About this module. Module 4. AI classifies images. Introduction. In this module, you'll learn how AI can not only analyze images to identify their contents, but create believable images by itself. Learning objectives. After completing this module, you should be able to describe how AI classifies images to derive meaning from them. Describe how a convolutional neural network, CNN, analyzes an image. Describe how a generative adversarial network, GAN, creates a credible image. Identify real-world uses for computer vision. Convolutional neural networks. An AI system uses a convolutional neural network, CNN, to analyze images. Digital photos and videos build images with millions of pixels, tiny dots that, taken together, give the human eye the illusion of a two-dimensional image. Each pixel has one of several million brightness and color levels that can be expressed in numbers. A computer, including the camera in a cell phone, can look at each of those pixels and input or output its numbers, either recording, input, or displaying, output, an image. But it's one thing to display an image and another, much more complicated thing to analyze it. The problem is caused by those millions of pixels with their color and brightness levels. They add up to numbers so large that they would overwhelm most AI systems. Research scientists say that too much data can flood a system. To get around this, research scientists have devised a clever way to analyze only small parts of an image at a time. This process, called a convolutional neural network, or CNN, makes it possible for visual recognition systems to identify things in an image, as in facial recognition. Martin Keen, an IBM master inventor, understands how a convolutional neural network brings image analysis down to a practical scale. What are convolutional neural networks? Video transcript. Okay, pop quiz. What am I drawing? I'm going to make 3 predictions here. Firstly, you think at your house, you'd be right? Secondly, that just came pretty easily to you, it was effortless. And thirdly, you're thinking that I'm not much of an artist, and you'd be right on all counts. There. But how can we look at this set of geometric shapes and think, oh, how? If you live in a house, I bet it looks nothing like this. Well, that ability to perform object identification that comes so easily to us does not come so easily to a computer, but that is where we can apply something called convolutional neural networks to the problem. Now, a convolutional neural network, or a CNN, is an area of deep learning that specializes in pattern recognition. My name is Martin Keen, and I work in the IBM garage at IBM. Now let's take a look at how CNN works. At a high level. Well, let's break it down. CNN, convolutional neural network. Well, let's start with the artificial neural network part. This is a standard network that consists of multiple layers that are interconnected, and each layer receives some input, transforms that input to something else, and passes an output to the next layer. That's how neural networks work, and CNN is a particular part of the neural network, or a section of layers that say it's these 3 layers here. And within these layers, we have something called filters. And it's the filters that perform the pattern recognition that CNN is so good at. So, let's apply this to our house example now. If this house were an actual image, it would be a series of pixels, just like any image. And if we zoom in on a particular part of this house, let's say we zoom in around here, then we would get, well, the window. And what we're saying here is that a window consists of some perfectly straight lines. Almost perfectly straight lines. But, you know, a window doesn't need to look like that. Window could equally look like this, and we would still say it was a window. The cool thing about CNN is that, using filters, CNN could also say that these 2 objects represent the same thing. The way they do that, then, is through the application of these filters. So, let's take a look at how that works. Now, a filter is basically just a 3x3 block. And within that block, we can specify a pattern to look for. So, we could say, let's look for a pattern like this, a right angle in our image. So, what we do is we take this filter, and it's a 3x3 block here. We will analyze the equivalent 3x3 block up here as well. So, we'll look at first of all, these first group of 3x3 pixels, and we will see how close are they to the filter shape. And we'll get that numeric score, then we will move across one, come to the right and look at the next 3x3 block of pixels and score how close they are to the filter shape. And we will continue to slide over or vote over all of these pixel layers until we have not every 3x3 block. Now, that's just for one filter. But what that will give us is an array of numbers that say how closely the image matches filter, but we can add more filters, so we could add another 3x3 filter here. And perhaps this one looks for a shape like this. And we could add a third filter here, and perhaps this looks for a different kind of right angle shape. If we take the numeric arrays from all of these filters and combine them together in a process called pooling, then we have a much better understanding of what is contained within this series of pixels. Now that's just the first layer of the CNN. And as we go deeper into the neural network, the filters become more abstract, and they can do more. So, the second layer of filters perhaps can perform tasks like basic object recognition. So we can have filters here that might be able to recognize the presence of a window or the presence of a door or the presence of a roof. And as we go deeper into the CNN to the next leg, well, maybe these filters can perform even more abstract tasks, like being able to determine whether we're looking at a house or we're looking at an apartment or whether we're looking at a skyscraper. So you can see the application of these filters increases as we go through the network and can perform more and more tasks. And that's a very high level, basic overview of what CNN is. It has a ton of business applications. Think of OCR, for example, for understanding handwritten documents. Think of visual recognition and facial detection and visual search. Think of medical imagery and looking at that and determining what is being shown in an imaging scan. And even think of the fact that we can apply a CNN to perform object identification for badly drawn houses. If you have any questions, please drop us a line below, and if you want to see more videos like this in the future, please like and subscribe. Thanks for watching. To summarize, in a CNN, two small groups of pixels that overlap each other are compared mathematically to get a value. AI can use thousands of these small comparisons to identify individual parts of an image, then compare them to images in its corpus. From this, AI can put together an overall identification, without being overwhelmed. Generative adversarial networks. A visual recognition system can use a generative adversarial network, GAN, to create new drawings and photos. Recall that an AI system can analyze a photo using a neural network to identify a photo. But what about AI systems themselves that create imaginary photos? You might have heard of computer-generated deepfakes, computer-generated images that look like they were taken from real life. You might have also seen drawings or handwriting created by AI artists. How does a system do this? One way is by pitting two convolutional neural networks, CNNs, against each other in a contest called a generative adversarial network, or GAN. In effect, the CNNs battle each other until one of them becomes pretty good at creating art. Martin Keen returns to explain the surprising way a generative adversarial network does this. What are GANs? Video transcript. One of my favorite machine learning algorithms is generative adversarial networks, or GAN. It pits two AI models off against each other, hence the adversarial part. Now, most machine learning models are used to generate a prediction. So, we start with some input. Training data, and we feed that into our model. A model then makes a prediction in the form of output. And we can compare the predicted output with the expected output from the training data set. And then, based upon that expected output and the actual predicted output, we can figure out how we should update our model to create better outputs. That is an example of supervised learning. A GAN is an example of unsupervised learning. It effectively supervises itself, and it consists of two submodels. So, we have a generator submodel, and we have a discriminator submodel. Now, the generator's job is to create fake input or fake samples. And the discriminator's job is to take a given sample and figure out if it is a fake sample or if it's a real sample from the domain. And therein lies the adversarial nature of this. We have a generator creating fake samples and sending them to a discriminator. The discriminator is taking a look at a given sample and figuring out, is this a fake sample from the generator? Or is this a real sample from the domain set? Now, this sort of scenario is often applied in image generation. There are images all over the internet of generators that have been used to create fake 3D models, fake faces, fake cats, and so forth. So, this really works by the generator iterating through a number of different cycles of creating samples, updating its model and so forth until it can create a sample that is so convincing that it can fool a discriminator and also fool us humans as well. So, let's take an example of how this works with, let's say, a flower. So, we are going to train a generator to create really convincing fake flowers, and the way that we start by doing this is we need to, first of all, train our discriminator model to recognize what a picture of a flower looks like. So, our domain is lots of pictures of flowers, and we will be feeding this into the discriminator model and telling it to look at all of the attributes that make up those flower images. Take a look at the colors, the shading, the shapes, and so forth. And when our discriminator gets good at recognizing real flowers, then we'll feed in some shapes that are not flowers at all and make sure that it can discriminate those as being not flowers. Now, this whole time our generator here was frozen, it wasn't doing anything. But when our discriminator gets good enough at recognizing things from our domain, then we apply our generator to start creating fake versions of those things. So, a generator is going to take a random input vector, and it is going to use that to create its own fake flower. Now, this fake flower image is sent to the discriminator, and now the discriminator has a decision to make. Is that image of a flower the real thing from the domain, or is it a fake from the generator? Now, the answer is revealed to both the generator and the discriminator. The flower was fake and based upon that, the generator and discriminator will change their behavior. This is a zero-sum game. There's always a winner and a loser. The winner gets to remain blissfully unchanged. Their model doesn't change at all, whereas the loser has to update their model. So if the discriminator successfully spotted that this flower was a fake image, the lead discriminator remains unchanged. But the generator will need to change its model to generate better fakes. Whereas if the reverse is true and the generator is creating something that fools the discriminator model will need to be updated itself in order to better be able to tell where we have a fake sample coming in, so it's fooled less easily. And that's basically how these things work. And we go through many iterations of this until the generator gets so good that the discriminator can no longer pick out its fakes. And there we have built a very successful generator to do whatever it is we wanted it to do. Now, often in terms of images, the generator and the discriminator are implemented as CNNs. These are convolutional neural networks. CNNs are a great way of recognizing patterns in image data and entering into sort of the area of object identification. We have a whole separate video on CNNs, but they're a great way to really implement the generator and discriminator in this scenario. But the whole process of a GAN isn't just to create really good fake flowers or fake cat images for the internet. You can apply it to all sorts of use cases. So take, for example, video frame prediction. If we fit in a particular frame of video from a camera, we can use a GAN to predict what the next frame in this sequence will look like. This is a great way to be able to predict what's going to happen in the immediate future and might be used, for example, in a surveillance system. If we can figure out what is likely to happen next, we can take some action based upon that. There's also other things you can do, like image enhancement. So, if we have a kind of a low resolution image, we can use a GAN to create a much higher resolution version of the image by figuring out what each individual pixel is and then creating a higher resolution version of that. And we can even go as far as using this for things that are not related to images at all, like encryption. But we can create a secure encryption algorithm that can be decrypted and encrypted by the sender and receiver, but cannot be easily intercepted, again by going through these GAN iterations to create a really good generator. So that's GAN. It's the battle of the bots where you can take your young, impressionable, and unchanged generator and turn it into a master of forgery. If you have any questions, please drop us a line below. And if you want to see more videos like this in the future, please like and subscribe. To summarize, a GAN battle ends with an image that's ready to be shown to a human. Sometimes, the human might laugh and think the resulting image is ridiculous. But other times, the human, like the CNN acting as judge and teacher, won't be able to tell the difference. At that point, the deep fake is a success. Computer vision applications. Computer vision has many useful applications. Here's just one application of computer vision that, working behind the scenes, can save lives. Diagram of suspension bridge with inspection drone and monitor camera. The IBM Maximo visual inspection system can be equipped with video cameras on drones. It can not only detect problems, like cracks in a suspension bridge, but identify which problems, cracks, in this example, are dangerous and should be repaired. Reflection: what do you think? Think about AI computer vision in your life. Take a moment to list at least one way that computer vision impacts you personally. Evaluate your thinking. Does your answer account for the following? Here are more applications that you might not have thought of. Spotting a dangerous but difficult to detect flaw in an airplane's wing. Monitoring water flow across a dairy farm to ensure it doesn't reach nearby food crops. Counting the number of people in an unruly crowd. Classifying animal and plant populations to measure biodiversity in a forest. Performing lip reading for people who cannot hear or speak. Although you might think these applications of computer vision might not affect you, they have the potential to benefit you, guide you, or even save your life. You've come so far and learned so much. You learned how artificial intelligence systems understand and work with human language and how they classify and extract information from pictures. Now that you've completed this course, you should be able to define natural language processing. Explain how AI uses natural language processing to derive meaning from text. Explain the classification problem and its solutions. Describe how a chatbot hears, identifies, and responds to a question. Distinguish between intents, entities, and dialogs. Identify appropriate uses for chatbots. Identify real-world uses for natural language processing. Describe how AI classifies images to derive meaning from them. Describe how a convolutional neural network, CNN, analyzes an image. Describe a generative adversarial network, GAN, creates a credible image. Identify real-world uses for computer vision. Key points to remember. 1. Machines require systems called natural language processing, NLP, to understand human language. Human language is unstructured. In NLP, machines segment sentences into small chunks of information, called a token. Machines classify and sort tokens into a structure so NLP can work with them to extract meaning. 2. With IBM Project Debater, the goal was to build an AI system that could help people make evidence-based, bias-free decisions on difficult topics where the answers aren't obvious. 3. The 4 steps a debater AI system takes include: Step 1. Learn and understand the topic. Step 2. Build a position. Step 3. Organize your proof. Step 4. Respond to your opponent. 4. Emotion detection identifies distinct human emotion types. AI can be trained to classify emotions. 5. Sentiment analysis is a measure of the strength of an emotion. It results in assessing if data is positive, negative, or neutral. 6. Chatbots are ready to answer your questions. The front end interacts with the person asking questions. It listens, or reads, and speaks, or presents text. The backend operates application logic and has enough memory to remember earlier parts of a conversation as dialogue continues. 7. A chatbot identifies entities and intents, then uses what it has found to trigger a dialogue. An intent is a purpose, or the reason why a user is contacting the chatbot. Think of it as a verb or action to take. An entity is a person, place, or thing. Think of it as a noun. A dialogue is a flowchart that illustrates the chatbot replies to the user intents. 8. With a convolutional neural network, CNN, an AI system can analyze images. With a generative adversarial network, GAN, an AI system can create new drawings and photos. 9. NLP and computer vision can be useful ways to extend human expertise. Explore more. To explore topics from this course in greater depth, check out these resources. Opens in a new tab. Opens in a new tab. What is natural language processing, NLP? Opens in a new tab, an IBM site that explains NLP tools and use cases. What is a chatbot? Opens in a new tab, an IBM site that explains chatbots and sets out guidance for making them more effective. What is computer vision? Opens in a new tab, an IBM site focusing on computer vision and how AI derives meaningful information from digital images, videos, and other visual inputs.